Why wouldn't they?
Yeah, why is it? Well, when would they ever show up?
Why not?
Be specific. Modeling population. How about harmonic motion? Particularly damped harmonic motion? Or I've got a sinusoidal wave. Well, it's not really sinusoidal. It's a sine wave whose amplitude is decreasing down to zero. Or maybe an example of a sine wave who's affected by some outside force where the amplitude is increasing without bound. That happens when you overrun the natural frequencies of a system. Sorry, I'll come back. The question, can we find A inverse? And to find A inverse, actually, I don't know how to do this. You guys got to direct me. Do you want me to do it the long way or you want me to use a shortcut, Michael?
I think I remember I used the shortcut only because it was a 2x2, but 38 was a 3x3, and so there was no shortcut.
Gotcha. But if you try shortcut in this one, let me try the shortcut as well. And in using the shortcut, I think A inverse is simply going to be a 2x2. Hold on, you guys, I gotta stop. A 2x2 where? Along the main diagonal, I'm merely going to swap entries. Would that give me this? And this? Whereas along the non-main diagonal, I'm going to keep the entries where they are. I'm just going to change everybody's signs. That's SIG and not SINE. Set positive e to negative t, cosine 2t. And then I've got my negative e to t. Cosine 2t. Oh shoot, I forgot my coefficient. I guess it's going to give me a coefficient outside. That's 1 over. The product down the main diagonal minus the product down the non-main diagonal. Let's start with the first. Along the main diagonal, these cancel by multiplication or division, whatever you want to call it. And I'm simply left with sine squared of t. Did I misspeak? I think it's sine squared of... Yeah, I said t, I meant 2t. However, I'm going to subtract off the product down the non-main diagonal, but again, you guys, via multiplication or division, I think these e's cancel each other out, and I'm merely left with a minus negative cosine squared of 2t. Oh, by the way, that coefficient looks really nice. What is it? It's just 1. And so I think in the end, if I can finish my bracket, in the end, I think I'm merely left with a 1 times something. And the something is simply going to be, oh shoot, yet again, product down the main diagonal. Minus the product down the non-main diagonal. Oh, you guys, this is looking nice. What do you think?
Everybody.
So is that a determinant?
That'd be the determinant. Well, that's
That's
my question.
nice.
Is this okay?
That's not a determinant, though, so why are you...
Yeah, I think what I did was perfectly fine if I had this. I'm just checking you guys up. Yesterday in class, I did change the subject to determinants, but this isn't one, is it?
No.
And if it's not a determinant, what do we do next?
Then you could just scale it if you want to by 1, so
Yeah.
it's just going to be equal to itself.
Okay, or I was hoping you say, just don't do anything.
Yeah.
But if you wanted to, I suppose you really could pull out a factor e to the negative t. I think that would work. And I get this. Just make sure I get the sign straight. What's wrong? And again, here too, if it were determinate, what I put on the board is mathematically correct. I pull things out of a single column or a single, row. But I confess I'm wrong. It really is a matrix, so I pull out the e to t, or e to the negative t. Did I write this down correctly? You guys, I made a more serious mistake. I'm being goofy here, but I think there's a more serious mistake. Yeah, I pulled out an e to the negative t. It gets pulled out here.
Yeah.
But I completely misread things. I thought that was e to the negative t here and here. No, I made that mistake. I'll fix it. And in fixing my mistake, I don't know. I'll be quiet. You fix my mistake.
Pull out an e to the t.
Then what do I get?
Then you're going to get a, basically a 1 on the outside, right?
I think e to the...
2t.
Yeah. If you wanted to pull out e to the negative t.
But if you pulled out an e to the t from the... Oh, you have to do it from...
Oh,
never
that's
mind.
fine.
You're tricking me.
And I'm just
Yeah,
checking
because
the
you were doing
difference
the
between matrices and
determinant.
determinants.
Yeah, and I was... Yeah.
And Brad, if you pull out e to the positive t,
Yeah.
this goes, this becomes e
Yeah.
to the
Negative.
negative 2t and
Yeah.
the same thing.
Yeah, yeah.
Sorry if I flipped it up, Mike. How about something, Michael, is that okay?
Yes.
How about something like 30, oh shoot, I said 38. So here's my matrix A. And if I'm going to find its inverse, well, okay, you guys, as of now, as of today, I guess we don't have any shortcuts. I'm going to have to augment this with the appropriate size identity matrix. I will then use my elementary operations to reduce what the heck you see on the left-hand side of the vertical bar to nothing more than an identity matrix. So, what do we do first? Force the first entry, first row, first column to be a piece of cake. I'm simply going to multiply through the first row by e to the negative 2. And I won't do anything else to the other rows together. I will next work on finishing my business with the very first column by forcing everything else in that first column not along the main diagonal to be a 0. Do you mind if I don't write this down? I'll just multiply the first row by negative e to t, add it to the second as well as the third.
Yeah.
For now, that first row is not going to change. Oh, I've got a 1t, it's e to the negative 3t, and e to the negative t. Alright, you guys, I gotta slow down now. Like I said, multiplying the first row by negative e to the t, adding to the second row, I think that's gonna give me a 0, as desired. Is that gonna give me a positive 1t e to t? That's gonna give me a, is that gonna be a 0? Is that gonna give me a negative 1? 1, 0. Playing the same game, multiplying the first row by negative e to the t, adding the third row, I think that's going to give me a 0. Oh, come on, am I going to go that fast? 0? Positive e to the negative 2t? Oh, I forgot the rest of my apologies. Is that going to be a negative 1, 0, 1? And I think in the second column, to force the entry along the main diagonal to be a positive 1, I'll just multiply it by 1 over t to the t. I think it's going to give me this. It's going to be a 0. Instead of 1 and then a 0. But that's going to give me a negative 1 over t e to the negative t, and then a positive 1 over t e to the negative t. And for now, nothing else is going to change. Well, for the first row, I mean, and for the third row. You guys, I did get a little lucky. I mean, technically speaking, there are a lot of extra zeros around here, so it does kind of cut down on some of my work. I do think this is the next beast I need to work on, but I can accomplish that task just by multiplying the second row by negative t, adding to the first, using the result as my new first row. And if I were to do that, here's the equivalent augmented matrix. I think my entries in the first row are going to be 1, 0. Okay, now I really do have to slow down. Is that going to be e to the negative 3t? Is that a... Did I forget a negative? My apologies, thank you. I thought we meant down the base. Does that give me a 2 e to the negative t? And then that'll give me an e to the negative t. Actually, it's gonna be negative.
Negative e.
And then it's gonna give me my 0 remains. My second row I like. Third row, I'll keep, actually, I take that back. Since I'm already here, can I just skip a step? First row, I'll force that entry and the third column to, third row, I'll force the entry in the third column to be a positive 1. I'll just multiply it through by e to the negative 2t, or excuse me, e to the positive 2t. See guys, I only have one step left. Forcing the entry in the first row of the third column to be a 0, I will have succeeded in forcing the identity matrix to exist to the left-hand side of the vertical bar. I just think I'm going to accomplish that by multiplying the third row by negative e to the negative 3t adding to the first. And I think that's going to give me, actually I have no idea what that's going to give me. I said negative e to the negative 3t. Is it a positive 3? So remember, I'm doing this. Negative e to the negative 3t times the third row, add it to the first, use the results of my new first row. I think likewise, C, who cares what times 0 plus this is just this, and it's negative. And lastly, multiplying this by e to the negative 3t, adding to my 0, oh jeepers, that's just going to give me negative e to the negative t. Oh, but nothing else changes. So it becomes, it's just a bit of bookkeeping, I think. Do you guys agree?
So I have a question really fast.
Yes.
So at number 15.
Same section.
Yeah, I mean, if I give you this is what I did. I went over this multiple times and I couldn't figure out where I went wrong. The book got such a nice answer and I got such a scary one. And number 15 in 2.6. 2.6.
You know what?
Yeah.
You're in a different section.
Yeah, I'm in 2.6.
My apologies. You said that, I didn't catch it. Ah, what am I doing?
Also, like, if I make just like a small error in one of these matrices, like how harsh are you going to be on grading something like that? I mean,
I really hate this.
yeah,
I'm just being honest. I can't stand grading this work.
yeah,
Because what I have a tendency to do, much to your advantage, much to my disadvantage,
yeah,
is I'll find your mistake.
yeah,
And then given that is correct, I go through and check all your other steps. And I will deduct points depending on how many additional errors you have.
okay,
Which really makes life miserable for me because if everybody gets it wrong, everybody's got a different answer, I gotta go through step by step.
So if
So please don't
you
make a mistake.
make,
Just write it in pen so you can't make any errors.
so if you make one mistake in there and then do everything else correctly, but that one mistake makes everything else wrong,
If the questions merely
Yeah.
come up with an inverse matrix or
yeah,
solve a system of equations, yeah.
okay,
Excuse me. Unfortunately, if you're trying to prove a mathematical statement and you end up using inverse matrices or Gauss-Jordan elimination,
then it won't work.
yeah, that would be more problematic.
But then if I try doing that, then I could see that I made a mistake and I went through. But if I did something like that and I couldn't look at the answer, I couldn't really see that it was wrong without going back through and retracing every single step, and
Sure.
that takes a really long time.
You can just ask him.
Yeah, and it would probably still take a while if I did that.
So you're in 2.6.
Yeah.
I'll look at it
Okay.
when we get time.
Okay.
I think it'd be instructive if I just do it now.
Okay.
Anybody else? Anybody have any questions? Pretty easy stuff, right? Do this for me. Let's see if I did everything right today. Be honest with a show of hands. You caught up in the homework?
Pretty close.
Oh, good. that's why I went to all the mechanics yesterday.
Monday I get home at 10, so it's my bad day for doing homework.
I can't attack you. I guess on Mondays I get home at 9 o'clock myself,
Yeah.
so, yeah, I see your point. Well, I maintained yesterday in class, I really did do a lousy job because I came into class and talked about determinants and didn't really tell you what they were. So now let me back up and go through some of the theory behind determinants.
What section is this? This one,
What section are we moving into?
This is called, collectively speaking, chapters 2 and 3. I'm sorry, it's hard for me to just dive in section by section. Besides,
Okay.
you guys, I'm intentionally doing a quick job on both these chapters. I think they're so light. I really want to dive into the vector space theory, which hopefully I can start today. We'll see how it goes. So you guys do this for me. If I asked you to consider Mike, Alice, and Brad, these are the only 3 people I want to discuss. And I got 3 chairs out there that I pasted the notes on the back of: President, Vice President, Treasurer. How many different ways can I rank these 3 individuals? How many different ways can I form a seating out there where one person's president, one's vice president, one's treasurer? How many different ways can I do that?
3 factorial.
President.
3 factorial.
Yeah, 6, which is 3 factorial. 3 times 2 times 1, because the number of people I can choose to put the first seat is 3. Wait, hold it. That's how many people I can choose for the first seat. That's not conducting the entire experiment. That's only performing one of the subtasks. So I take the number of ways I perform that subtask, I multiply the number of ways I perform that subtask by the number of ways I can perform the second subtask, which is choosing some for the second seat. There's only 2 people left. Times the number of ways I can perform the third subtask of choosing a treasurer, but there's only 1 person to choose from. And so I guess it'd be 3 times 2 times 1, which is 6. So I think there are 6 different permutations. Actually, let me restate that. When it comes to numbers 1, 2, and 3, I think here's one permutation of those numbers. I think another one might be 1, 3, 2. I think another might be 2, 1, 3. I think another might be 2, 3, 1. I think those are all the permutations. Oh, I misspoke, didn't I? My goodness. I forgot mine. 3, 1, 2. Jeepers, I can't even write it. And I forgot my 3, 2, 1. I'm sorry, you guys. I just lost train of thought. Something came in my head. Brad?
Yeah.
I went to curriculum committee for the
Okay.
college yesterday,
Yeah.
last night. And I got 15 put through. It passed. So it's done.
So, well, I'm still going in to talk to
No,
Willie
I
Duncan
just
tomorrow,
mean as
but
far as the college is concerned,
Okay.
it's now a viable course again.
awesome.
That's all.
Do you know when it's going to be taught?
Well, the argument I think you or Randall gave me is that they have to find some connection.
Not during physics. That's the only thing that
When's physics?
generally before noon or 1 or something like that. And then symbolic logic is at 12:30 to I think 1:30, something like that.
Well, maybe you guys in the math club should decide.
We could talk to people in the calculus club about
Yeah,
that.
and amongst yourselves, yeah,
Awesome.
and just go.
All right.
Now, are people thinking of getting that course running for next semester?
Yeah, that's what I've been hearing is they want to do it next semester.
So I don't know how to tell you this.
Yeah.
There's probably only 1 person who's willing to teach that class. There's
Yeah.
only 1 person taught for over a decade now.
Who's that?
So just so you know, I don't think anybody's going to teach it.
Okay. Yeah, that's good.
You guys, let me come in. Let me talk about this order of the numbers, 1, 2, and 3. Plant your feet at 1. Is that less than every one of the entries following it? Yes. What about 2? I think it is. I think there's no case in here in which I move left to right, these numbers, these digits are out of order. So I might say in English there's no inversions for this permutation. I might even use this notation. The number of inversions of this permutation is equal to 0. Sometimes I might subclassify that number. Since it's an even number, I might even say the original permutation within has even parity. Just a choice of words, you guys. It's just English. I think when it comes to this permutation, check this out. I think I've got one inversion. Because I think when it comes to 3, it's not less than what comes after it. So I might say the number of inversions is going to be 1. I might even subclassify that permutation as having odd parity. And you guys finish this up. What do you think?
Would it be 1 or 2? It'd be 1.
I just said it'd be 1 because only the 1 and 2 they're out of order. So I would have just said it's 1. What about here? I think it's 2. Because 2 is not less than 1 and 3 is not less than 1. You guys get the idea?
Yeah.
Can I play the French technique again then? So I think it'd be 2, isn't it? 3 is out of order with the 1, 3 is out of order with the 2. I think the number of inversions here, actually I have no idea, I've got to count. What do you come up with?
4.
Yeah, that's what I came up with 3. For the 3, there's 1, 2.
Yeah.
But for the 2, there's a third one. So it has odd, that permutation, I should say, English has odd parity. 3 there.
Yeah, I'm just trying to
Trying to 1.
figure out what this means. Like,
You mean what it's going to end up giving you?
yeah,
I think what I'm playing with in terms of numbers and permutations is going to give you an means by which we can clearly define what a determinant is. I came to class and was very hokey yesterday. I always seem to give you gimmicky ways of generating the value of a determinant. Now I just want to be more detailed with this so I can talk about some consequences, some properties of determinants.
okay.
Well, if I take the permutation 1, 2, and 3, I might want to sometimes refer to it in some sign. Oh shoot, if I can make up this whole word an English sign, I guess I better use the letter S. That looks awkward, do you mind if I don't? Let me steal from the Greek alphabet.
Sigma.
It kind of looks awkward too, doesn't it? I mean, it looks like I'm dealing with a sum of things. How about if I steal the lowercase Greek letter sigma? And if I talk about the sign of a permutation,
Wait, isn't that squiggly D?
You don't like my sigma?
Is that squiggly D or sigma?
It's the other way.
Squiggly D's the other way. Okay, all right.
Squiggly D, what's squiggly D?
Squiggly D's the other, partial fraction
Partial derivative.
or partial derivative. Partial
Something
derivatives.
like
Yeah.
that.
Yeah. Okay. It looked like squiggly D for a bit.
Just imagine I'm a statistician and treat that as a standard deviation.
Okay.
So I think the sign of a permutation is going to be nothing more than -1 raised to the number of inversions, the parity of that permutation. And I think in this particular example, the sign of this permutation is going to be -1 to the 0, but that's just going to be 1. I think the sign of this permutation will be
To the 1.
which is
Negative
-1. -1. +1 as well as here, but -1. And so the sign of a permutation can only hold one of the two values, +1 or -1. Are you with me? If you are, then, shoot, how can I say this next? Let's talk about the 2 by 2 determinant. And if I were to divide this 2 by 2 right here, you guys hear me for a minute. I'm just trying to lead into a more general definition of what a determinant really is. Could you guys do this one in your head? Hold it. No, don't do it in your head.
Yeah.
I need color. Just
A1, A2 minus
any color. So say it again. It goes
A11 times
A11
times A22 minus A21 or A12 times A21.
Okay, I've got 2 terms. I want you to look at the subscripts and pay attention to what you see in black. With the number of rows I'm in, aren't the rows constantly increasing? 1, 2, 1, 2.
Yep.
But notice how the column position is a combination of permutations I can have on 1 and 2. Notice that the parity here is,
1, 2.
the parity is
Parity is even.
even.
Good.
So the sign's going to be
1.
Oh. No sign change. But just parity on the position of the columns
Is
is
odd.
odd, and so the sign will be
Or
negative one. Oh, look, the sign changed, maybe I can incorporate that in my cofactor expansion prescription. Let's do it again. I think if I were to look at A11, A12, A13, A21, A22, oh, I'll keep going. Here, if I were to list out this particular evaluation, I know I didn't give you a shortcut, but that was a shortcut for inverse matrices anyways. As far as a term is concerned, check out what you got. You guys, I'm going to be a little slow because I'm using color.
Wouldn't it be A33?
Say it again.
Wouldn't it be A33?
It certainly would. Thank you. I'm counting in red, but miscounting in black.
Okay.
So you guys, I'm not finished. But with these three terms, check out what happens when it comes to the sign of this permutation on the position of the columns. The sign will be,
Yeah,
parity's even,
even.
which is sign is. Sign is
Odd.
It's
positive one,
It's positive one.
because I got 1, 2 inversions.
Oh, okay.
Sorry, I meant to, 1 and 2 inversions. Here, the sign of the permutation is going to be
Negative one. No, it's positive.
That's gonna be odd.
positive 1. Oh, look at that. All my terms are positive. But you know what? I'm not done. This is not my working definition of a 3x3 determinant evaluation. I'm missing a few terms. I've got an a sub 1, 1 times a sub 2, 3 times a sub 3, 2. Oops, I messed up. How about an a sub 1, 2? A sub 1, 3. Excuse me, a sub 2, 3. I can't, that's the same as what I had. A sub 2, 1. And finally, an a sub 3, 3. And lastly, I've got one more term, namely a sub 1, 3, a sub 2, 2, and then finally a sub 3, 1. Let's talk parities. I think in terms of parities, I don't know. You guys, give me the parity here.
Odd.
I think the parity here is going to. Sorry, I'm so slow. It's definitely going to be odd because it's only one inversion. Oh shoot, that means the sign is negative 1. I'll get a sign change. I think in terms of parity here, can we check things? There's one inversion. And then, is that it? So I guess the sign of that permutation is going to be negative 1. And lastly, the number of inversions is going to be 1, 2, actually 3. And so negative 1 to the third power is going to be negative. This is how I'm going to make a decision on whether or not I got a positive or negative term when I expand out these determinants of whatever size you might have. Well, I back up. They got to be of square matrices for them.
What are the red subscripts on the lower row, from left to right?
You know, all I'm saying is that I listed out here, if you keep the position of the rows constant, then what you see in red are the positions of the columns. And what you see in red are 1, 2, 3, 4, 5, 6 possible permutations of the numbers 1, 2, and 3. And when it comes to the column positions, if I permute those, then I think I've got 6 possibilities. And I'm going to change the sign of the term, of these 6 terms, change the signs to negatives, if it's the case that the parity is odd when it comes to the column position for each and every one of these 3 pieces downstairs. But the parity was even for the first 3 terms of my expansion.
So, really quick, can you just circle in the determinant what you did to expand that? I'm pretty sure I'm seeing it. You just took the column going down, then you took the other column plus the A on the end. You see what I'm saying, though?
That's not what I did.
Okay.
In my head, I foresee the issue of creating 3 even parities.
Okay.
Did you guys see how slow I was down here with the last 3? In my head, the reason I was slow, because I don't memorize anything. I just kept the first column position same, and I just interchanged these 2. Kept this column position same, interchanged these 2. kept this column the same, interchange these two, just to generate all 6 possible permutations of the numbers 1, 2, and 3. That's what I did in my head. Brad, let me show you what you're thinking. It's something I
Yeah.
never said in class.
Okay.
What you're thinking of is a shortcut
Yeah.
to evaluating a 3x3 determinant,
Yeah.
which I don't ever like to write, but since you asked, I'll write it once, just once.
I just haven't really seen
just
it
looks
yet,
goofy.
so.
But here it is. And I'm being honest, this is how some people actually evaluate 3x3 determinants. See the first column? I'll duplicate it on the outside. See the second column? Here too, I'll duplicate it on the outside. And I think that very first term over here is nothing more than the product of these 3 entries, plus the product of these 3 entries, plus the product of these 3 entries. Those are the first 3 terms. The last 3 terms involve minus the product down this odd diagonal, minus a product here, minus a product here. So if you want a gimmicky way of actually listing out those 6 terms, that would be one gimmicky way.
Oops.
It works. It's
Yeah.
just every time you see one of the green arrows, you got a negative sign out front because of the parity again.
Okay.
And for the blue ones, you've got a positive product. And if you want to use this Math 32 to compute cross products, it works just the same.
Okay.
Who cares if the first row consists of not entries that are real numbers, but unit vectors, the same thing happens. Oh shoot, you guys, I'm being so long-winded. You know what? I think I can finally do this. I think I can formally define what a determinant really is. Not a 2x2, not a 3x3, but any dimension n by n. I think the determinant of matrix A is the following. We will define the determinant, and I can spell that. The determinant has nothing more than a sum. Now the sum's going to have a factor of 1 or negative 1, depending what the sign of a permutation is, so let me put that factor in. I've got the sign of a permutation P1, P2, all the way down to Pn. Times a sub 1 something, times a sub 2 something, all the way down to a sub n something. Where the something, it's going to be P1, P2, all the way down to Pn. In other words, I'm actually listing a permutation on the column position of each and every one of these entries. And if you guys don't mind, because it's more complex, can I suppress saying what n's doing? Can I just say that we are summing over the n factorial permutations of the form P1, P2, all the way up to Pn. That is going to be my formal working definition of what the heck a determinant really is. So it's, if you get the idea of what I'm referring to as the parity of a permutation and its sign, otherwise my definition doesn't make sense. Okay, as long as you're happy. So do you guys think, I can play around with this. Let's just suppose I have an entire row. I'm not going to tell you which one. If I have an entire row completely of zeros in an n by n matrix, what can you say about the corresponding determinant?
0.
Why?
You would use that row as the cofactor in all the...
Will you ever really use that row in every one of these now? I'll ask it again. Will you be using an entry from that row for every one of these elements in this big sum?
Yeah, right.
Yeah, you would. And so I think what he's saying is correct. So guys, without loss of generality, let's suppose the first row contains entirely zeros. That means a sub 1 comma, who cares what, is going to be 0. And as a factor in each and every one of these n factorial terms. So clearly the determinant is going to be 0 if I have a row of zeros, or even a row of columns for that matter, and an n by n determinant. Do you guys see my point? Can I say it that fast in terms of justifying it? Do something else. I'm not getting away from this, but going back to just simply permutation. Is there anybody in this room who's willing to tell me what the parity is of this permutation? Good.
You
The answer is You have
can't.
no clue, right?
Yeah.
You have no clue what it is, because I'm not telling you what these numbers are for P1, P2, P3. However, what if I told you that I'm going to take the same darn permutation, I'm merely going to interchange, how about these two entries right here, wherever they are. Now you guys check this out. If I plant my feet here at a piece of k plus 1, how many inversions are there here and after? I don't know. But you know, if I just interchange pk and pk plus 1, no matter which one's larger, doesn't that just introduce one more inversion?
Yeah.
And so I think these two permutations have different parity. If the first one's even, the next one is going to be odd. If this is odd, the next one's going to be even. I can even extend this to separating these two anywhere. If I interchange them, I'm simply going to change by one inversion, and therefore the sign of these permutations are going to change. If I take any two entries and interchange them. So that basically means this. Oh, can I just, this is a theorem, among many others, theorem. If B is obtained. Oh, we can't have hieroglyphics. If B is obtained by interchanging. Two rows, or for that matter, columns. Then I think what I've just argued as the determinant of one is going to be the additive opposite of the determinant of the other. In other words, determinants change signs if I interchange any two rows and columns, just because the number of inversions changes by one when it comes to interchanging any two entries in some kind of permutation. Oh, well, look at that. Permuting on the position of the column is exactly how I'm defining these determinants. So clearly it has to be true. Can I not write this next one down? You guys understand that two matrices, two augmented matrices are equivalent if I replace one row with the multiple of itself. When it comes to determinants, however, since these represent real numbers, if I took this matrix B and replaced one of its rows with k times it, that's how it changes determinant. What's that? Why? Alright, that's a good way to put it. I'll say it a little backwards though. I think if I'm going to multiply one row, say for example by k, that just simply means without loss of generator, how about the first row? It means this particular factor becomes a k times a whatever it is. But that means I've got an extra factor k in all the terms, I can pull it out. So replacing a row with k times something else, replacing a row with k times it is going to change the determinant just by a factor of k. That's why in class yesterday, I said it unjustified, but I said, when it comes to determinants, if you want to pull out a constant from along one row or one column, it shows up on the outside once, which is different than matrices, where if I want to pull out a constant from a matrix, it's got to be pulled out of each and every entry of the matrix. That means every row or every column, not just one row or just one column. I'm just justifying it with this definition. What do you guys think you could say, just intuitively, relative to yesterday, what could you say about this?
It's, well,
Yeah, go slow. Think about this. This is important. I want to finish my theory today, so I just want to make sure this is all clear.
so if you move the first two rows onto the outside, then it's going to be equal to 0, right?